Today we're building a linear regression model from scratch in Python, no scikit-learn, just the mathematical implementation and code. This is part 2 of episode 1 of machine learning from scratch. If you want the theory, please make sure to look at part 1 first. Let's get straight to it. So first of all, I'm going to give a very quick recap of the theory first. The goal of linear regression is simple. We have a cloud of points, and we want the best fitting straight line that goes through this data. And that is supervised algorithm. Why supervised? Because the data includes both the input and the correct answer, the correct output targets. Once trained, the model can predict y hat for any unseen values of x. The line is f of x equals wx plus b, where w is the slope, how steep the line is, and b is the intercept, where the line hits the y-axis when x is equal to 0. So if I change w, the line tilts, and if I change b, our bias, then the line slides up or down. And so training means that we're going to find the weight and bias that makes the line sit as close as possible to every point in the data set. And this version is called ordinary least squares, OLS, which is a fancy name for minimizing squared errors. And there's not going to be any particular extra penalty. Ridge regression, shrinking weights is all going to be covered in episode 2, since we don't need it in particular for the dataset that we're going to be looking at today, which only has one feature. How do we know which values of weight and bias are better? To pick the best values, we minimize a cost function, which we're going to write as j of w and b. We want y hat to be as close as possible to y for every point, and that's going to be the error, prediction minus target, where we square it for 2 reasons. 1, so that negatives don't cancel the positives, and b, because big mistakes get punished more this way. Then we add up all of these m points, divide them by 2m to take the average. And the extra 2 is a convenience. When we differentiate u squared, a 2 pops up, and the 1.5 in the front cancels that 2. So the derivatives stay clean this way. We have only 1 over m. So the full formula is going to be j of wb equals 1 over 2m times the sum of f of x I minus yi squared. And that's the mean squared error. It measures how well the line fits the data. J is a surface sitting over the WB plane. High cost is a hill, and low cost is going to look like a valley. So training is really when you're going to be walking downhill in that paraboloid. To minimize our cost function j, we use gradient descent. So we start with some value of weight and bias, and usually that value is going to be at 0. And then we take small steps that lower this cost and keep going until the cost is either low enough or it stops changing. When the cost stops changing, that's when we're done, and that's what's called convergence. We found the bottom or close enough. The gradient is the slope of j, and it always points uphill in the direction of the steepest increase. But we want to decrease, so we step in the opposite direction of the gradient. And that's why we have a minus sign. So at every iteration, we're going to update our w and our b. So it's going to look like w minus alpha of the derivative of j over derivative of w, and b becomes b minus alpha times dj over db. And these are being updated simultaneously. Here alpha is going to be the learning rate, so the step size. And if you take an alpha value that is too small, then you have tiny steps that take forever to reach the bottom, and the cost barely moves. But if you have a alpha value that is too large, then you might overshoot and never properly settle for the minimum. So the ideal value of alpha is a value where the cost drops fast and then flattens. And in these formulas, we have 2 derivatives of j with respect to w and with respect to b. So what they look like is, for d of j with respect to weight, we have 1 over m times the sum of error times x of I. And then for the derivative of j in terms of b, then we have 1 over m times the sum of the errors. So b's derivative does not multiply by x. The intercept is a constant added to every prediction, so x doesn't show up. So this is the entire algorithm. Now let's get to coding. So first we're going to import our libraries. So NumPy for arrays, pandas for reading the CSV, and matplotlib to plot our graphs. So we're going to use a dataset from the textbook called An Introduction to Statistical Learning, called ISLR also in short. And so it has 200 markets, and for each market we know TV advertising budget and we know the sales. So X is our independent variable TV spend in thousands of dollars, And y is our dependent variable, units sold in thousands. So here we're going to create our data frame variable using pandas.readCSV. And I'll pull the two columns as NumPy arrays so that we can loop over them later. So we have our X raw for the TV values and our Y for sales values. And we can print some general information about the dataset that we're looking at to have a better idea of what we're dealing with. So I'm going to start with the head, and then we're going to look at what values it ranges from for the minimum and maximum, and how many markets we're looking at. And also looking at the cloud before we train will give us a nice idea of the relationship between these two variables. So we're going to do that with a scatter plot and label our X and Y values, and let's take a look at what it looks like. So you can tell there's an upward trend. The more TV ad budget is, then the more sales you have. And that's a relationship we want the line to learn. The data looks quite noisy. There's a lot of dots that are scattered everywhere, so it won't be possible to get a perfect line in this type of scenario. But here, linear regression seems like it will work really well as an initial model for this dataset. Before we start training, there's one small problem we need to fix. So look at the scales of our data. TV advertising ranges from 0 to 300, while sales range from 2 to 27. And why does that matter? Let's take a look at the gradients that we derived. The gradient for the slope multiplies by x, and the gradient for the intercept doesn't. TV values are on the order of 100 to 300, and the derivative of j with respect to the derivative of w contains the product with x of I, so it is huge compared to when you look at the derivative of j with respect to b. So when learning rates cannot take a sensible step in both directions, because if it gets multiplied by like something around like 150, well, the one with respect to b won't get multiplied by that much. You basically have old weight minus alpha times a huge number, and then the update for b would be the old value of b minus alpha times a much smaller number. So you can easily have a w that overshoots and the cost exploding, or the opposite, where if alpha is really small, to keep w stable, then b might barely move. And so the fix is to standardize x, and we leave y exactly as it is. So let's take a look at the formula for the z-score scaling, where mu is the mean of x and sigma is the standard deviation. And so when you look at the mean of this data set, it is of 147.0425, and the standard deviation is of 85.6393. After scaling, x will have a mean of 0 and a spread of 1. We will still predict original sales y, and after training, we convert the weight and bias back to per $1,000 of TV units. So after scaling, a scaled x mean of 0 means an average TV spend, and of plus 1 means one standard deviation above average, so about $86,000 extra. Most of our data now falls between minus 2 and 2 instead of 0 to 300. So then the derivative of j with respect to the derivative of w no longer gets multiplied by 150. It gets multiplied by a number around 1, in the same order as the derivative of j, the cost function, over with respect to the derivative of b. So one alpha or one learning rate will be able to work and update these two values simultaneously, because they're going to be on a similar scale. And notice that we only scaled x. Sales stay in their original units, so every prediction is still measured in thousands of units sold. The catch is, the way that we learn is now sales per standard deviation of TV and not sales per thousands of dollars, which isn't very intuitive. And after training, what we're going to do is that we're going to convert everything back to the original units with two simple lines of algebra. For now, let's print the mean, standard deviation, and verify that our scale data has a mean close to 0 and a standard deviation close to 1. Once that's true, we're ready to train. So yeah, our scaled mean is at 0 and our scaled standard deviation is at 1, so we're good to go on to the next step. So from scratch, we're going to need three functions. First, we have our cost, how long is the current line. Second, the gradient. It tells us which direction to move, weight, and bias to reduce that cost. And third, our gradient descent. That is the loop that repeatedly computes the gradient, updates the parameters, our weight and bias, and keeps going until the cost stops improving. Let's start with the cost function. So compute cost will take four inputs, x, y, w, and b. And first, I compute m. So that's going to be computed by taking the length of x, and that gives us a number of training examples. In our case, that's going to be 200 markets. Then I create a running total and initialize it to 0. Now we loop over every training example, and for each one, we calculate the prediction, w times x plus b. So we calculate our predicted value of f with the current value of x in iteration. Next, we compute the error, prediction minus the actual sales, and we square that error, add it to the running total cost. And once we've processed every market, we divide by 2m and return the result. And that number is going to give us a cost total, j. And I've said this before, but I'm going to keep saying it again. The smaller j is, the better our line fits the data. Now, compute gradient looks very similar to our previous function. It also takes the same inputs, x, y, w, and b. And we're going to obviously also start with getting to know the number of training examples with length of x. And we initialize our derivatives of j with respect to w and b to 0. So we start with looping through every training example. But the difference between this function and the previous cost function is what we're accumulating. Instead of adding squared errors, we're building the two derivatives each time. So we calculate the prediction and the error exactly as before. For the slope, we add errors times x, because the derivative with respect to w still contains that extra x. And for the intercept, we only add the error. After the loop, we divide both totals by m, not 2m. Remember, the factor of 2 disappeared when we differentiated the squared error. Finally, we return both gradients. Those are the numbers gradient descent will use to update the model. This is the function that actually trains the model. We pass in our data x and y, an initial value for w and b, the learning rate alpha, and the number of iterations. I also create an empty list called cost history. After every update, we'll save the cost j so that we can plot it later. So now comes the training loop. Each iteration is one step downhill. First, we call compute gradient using the current values of w and b. That gives us two gradients. Then we update simultaneously the two parameters. So w becomes w minus alpha of derivative of j with respect to the weight, and b becomes b minus alpha times the derivative of j with respect to b. And the minus sign is important because the gradient points uphill, but subtracting it will move us downhill, where the cost is at the minimum. And after updating the parameters, we compute the new cost and save it to our history. Every 100 of iterations, I print the iteration number, the cost, and the current values of w and b. As training progresses, we should see the cost drop quickly at first and then eventually level off. When the loop finishes, we return the final w, the final b, and the complete cost history. And this is the kind of optimization process that scikit-learn is doing under the hood in a single fits call. Now let's train the model. Our learning rate is 0.1. We're going to run 400 iterations, which is more than enough now that the feature is scaled. Well, we're going to start with both parameters equals to 0. Now watch what happens. At the beginning, the cost is huge. The model is basically a flat line, so the predictions are terrible. But after about 100 iterations, the cost has already dropped to 5.26 roughly. And then notice how it barely changes. At iteration 200, 300, 399, it stays almost identical. And that is exactly what we want. That is when the algorithm has converged. At this point, taking more steps won't improve the solution in any meaningful way. And if the cost had started increasing instead, then our learning rate would have been too large. If it barely moved after hundreds of iterations, the learning rate would have been too small. And remember, we trained using the scaled version of x. That means our learned parameters are expressed in standardized units, not dollars. So to make them meaningful again, we have to convert them back. The formulas are pretty simple. W original equals W divided by sigma, and B original equals B minus W times mu divided by sigma. So now we get sales equals 0.0475 times TV plus 7.0326. So now it's much more intuitive to actually interpret it, because for every additional $1,000 spent on TV advertising, the model predicts roughly 47.5 additional units sold. The intercept tells us that even with zero TV spending, the model still predicts about 7,000 units sold. Which is pretty reasonable because, products can still sell because of brand recognition, repeat customers, or other factors that aren't in our model. These coefficients match the value reported in the ISLR textbook, which is a pretty good sanity check. This means that we've successfully reproduced the same linear regression from scratch. Now let's take a look at R squared. Here R squared is about 0.1. And remember, R squared is simply a score that tells us how much of the variation in sales our model explains. In this case, it's about 0.61, so 61%, which is pretty low, but it's actually a pretty solid result for a real-world marketing data. And What we can say is that the remaining 39% most likely comes from everything else that we didn't include, such as radio advertising, ads that were run on newspaper, pricing, competition, seasonality, and even just randomness itself. And one more important thing to notice is that this model shows an association between TV advertising and sales, but it does not by itself prove that TV advertising causes those sales. Regression is going to find relationships, but it doesn't establish causation. Now let's take a look at the finished result. So on the left, every dot represents one market, and the red line represents the model that we just learned. Notice that it follows the overall trend without trying to pass through every single point, and that is exactly what we want. A good regression line captures the pattern, and not every bit of noise. On the right, we have the cost over time, and it shows that the optimization is actually working. The cost drops rapidly at first, and then it gradually flattens out, and that is gradient descent converging. If this curve had started going upwards, that would usually mean that our learning rate was too large. So that's linear regression from scratch. We have sales equals 0.0475 times TV plus 7.0326 in this case. But it will be completely different numbers with a different dataset, of course. So to recap, we started with a dataset of 200 markets. We built a linear model, f of x equals wx plus b. We measured the error using the cost function. So j equals 1 over 2m times the sum of squared errors. Then we repeatedly updated w and b by moving in the opposite direction of the gradient until the cost stopped decreasing. And that is the entire training process. In the next episode, we'll move beyond a single feature. We're going to add multiple inputs, split our data into training and testing sets, and introduce rich regression, where we add a penalty term to help prevent overly large weights. If you found this helpful, please consider leaving a like and subscribing so you don't miss episode 2. Thank you so much for watching. Bye.